Hi everyone. Today we have Dr. Lorena Moscardelli presenting in our AAPG South Basins webinar. Her talk is going to be about salt formations in their role as H2 storage real estate. Dr. Lorena Moscardelli is a research scientist and leader of the State of Texas Advanced Resource Recovery program at BEG. Her expertise is in seismic geomorphology and interpretation, sedimentology and stratigraphy, and geoscience data integration. She received a degree in geological engineering from Central University of Venezuela and a PhD in geological science from the University of Texas, Austin. She specialized in the study of deep water deposits with emphasis on subaqueous landslides, deep water mixed siliciclastic carbonate systems, and planetary geology. She started her career as an exploration geologist working for PDVSA from 2000 to 2003. Prior to her current position at STAR, Dr. Moscardelli was a principal researcher at Equinor from 2013 to 2021, where she performed a wide range of activities from research in the Americas to field development in the Norwegian continental shelf. Her BEG career includes the co-funding and co-direction of the Quantitative Clastic Laboratory from 2007 to 2013, and her actual involvement as a leader of STAR. Most recently, Dr. Moscardelli has taken a strong interest in understanding the role of geoscience research as part of the ongoing energy transition, while contributing to STAR's main mission of conducting geological research, resulting in the increase of production and profitability of energy resource in the state of Texas. So thanks, Dr. Lorena Moscardelli. It's a pleasure to have you here today.
Thank you for the invitation. I'm really pleased to be here, and good morning, good afternoon, good evening to everybody from wherever you're joining. Thank you for making the time to join my presentation. So I'm assuming that you can hear me well and you can see my slide. Yes, good. Yeah. So, I think this presentation is going to be interesting for this group because I'll tell you right now, this is not about salt tectonics. It is about how salt formations and salt tectonics actually can play an important role on this ongoing conversation about the energy transition. So it will be very heavy, I think, on the application component of things. I also want to acknowledge that, there are contributions from a large group of people here at BEE. I'm listing here some of the collaborators, but there is a broader group of people from different groups, also including postdocs and so on, okay? So I think this doesn't work too good. Okay, so, hydrogen. We have been hearing about hydrogen for now a couple of years, I think, or more. And the question is why hydrogen is important as part of a low carbon economy. And this is an illustration put together by DOE that tries to show a little bit about the ecosystem and the different components that are part of this hydrogen economy. I'm not going to dive too deep into this, but the main thing here is that hydrogen can help us decrease our carbon emissions. Keep in mind that hydrogen is not an energy source per se. It's an energy carrier for the most part, meaning that we have to derive hydrogen from either hydrocarbons or water. So the idea there then is that hydrogen can help us energize our systems, decreasing the amount of carbon emissions to the atmosphere. But in order to do that, we need huge amounts of hydrogen, and conventional storage in the way of batteries, for instance, are not going to make it, or tanks or surface infrastructure. So this is where geological storage plays an important role. In terms of hydrogen and energy equivalents, 1 kilogram of hydrogen is more or less equivalent to 1 gallon of gasoline, which is more or less equivalent to 33.3 kilowatt hours. The challenge here with hydrogen gas is that it has 1/3 of the energy as natural gas by unit volume. So we need 3 times the amount of hydrogen to generate the same energy that we generate with methane, for example. So volumetrically speaking, as you can imagine, there is a challenge. You have heard probably about all these hydrogen colors, and again, we can go from this end of the spectrum where we're talking about black or brown hydrogen derived from coal gasification without CCS or carbon capture sequestration, to green hydrogen in the other extreme of the spectrum, where we're talking about harnessing renewable energy, either by, we can think about solar or wind energy to energize electrolyzers that then break the water molecule to generate hydrogen and oxygen. In terms of CO2 emission reduction, we want to be in this end of the spectrum. The challenge here is cost. And the other thing that I want to highlight in here is that even though the science and the technology behind green hydrogen generation is there, is not to the point where it is economically viable for the most part. So this is one of the major challenges. And then we have a little bit in between, mainly blue hydrogen, which is essentially the same concept as gray hydrogen, using steam methane reforming or autothermal reforming to break the methane molecule and generate hydrogen and CO2. In the case of gray hydrogen, which is how we get our hydrogen today, the CO2 is released to the atmosphere, which is, not a good thing. But if we add carbon capture sequestration technologies into the process, and we capture that CO2 and inject it on the subsurface to sequester, then we're talking about blue hydrogen. Again, bringing this back to the concept of cost, some numbers here by the Department of Energy that shows you first that in the US, the ambition is to generate 1 kilogram of hydrogen per $1, by 2031. But in here, you can see how much it costs right now to generate hydrogen using coal gasification without carbon capture sequestration is a little bit north of $1. Autothermal reformer or reforming of methane without carbon capture sequestration. And then how the price starts to increase as we start to add carbon capture sequestration technologies to these industrial processes. And by the time we get to wind electrolysis or solar electrolysis, you can see that cost today per kilogram of hydrogen is pretty high. All right, so how much hydrogen do we need, right? And what are the projections and what are the ambitions? And this is 2020 right now, and this plot is showing you million metric tons of hydrogen. This is current consumption. Most of this goes into fertilizers and also in refineries to process hydrocarbons and to remove sulfur. And then these are some projections that go from base scenario to ambitious scenario to try to replace mostly hydrocarbons, right, from these energy systems. And if we look at 2050, right? If our ambition is to replace in the US 10% of natural gas, right, that we're using today, only 10%, we're talking about 14 TCF of hydrogen gas. So let's work with this scenario, because this is where I want to start to make the link with the subsurface and the storage story. So let's say that by 2050, we want to replace that 10% of natural gas by hydrogen. So if that is our ambition, right, we would need around 1,000 BCF, which is equivalent to 1 trillion cubic feet of additional hydrogen storage capacity. Today, in the US, we have between 5 to 8 BCF of hydrogen storage capacity. So what this means is that we would need to increase that storage capacity by a factor of 200 to only make a 10% replacement. So this is a big challenge, you know, and something to really think about. So I really like this plot because it's showing you the relationship between power and discharge time, okay? So when we are thinking about batteries, we are talking about power that goes between, I don't know, 1 kilowatt to 100 kilowatt in capacity. And we can release that energy when we're using batteries in a matter of hours. But when we're talking about gigawatt hour scale, you know, we need a whole lot more storage. And it is here where underground storage plays a role, because it would allow us to store in the gigawatt end of the spectrum and to release this energy on a matter of days, weeks, or months, you know. So to better illustrate this, I like to show this slide. So to the left, what you see is the Vistra Energy's lithium-ion battery system at Moscardelli Landing. In my knowledge up to today, I think this is the largest battery complex in the world that is fed by the grid currently. It has around 1.2 gigawatt hour of capacity that can be released in around 4 hours, or is 4 hours of storage duration. So remember this plot, we are in this field right here. And as I mentioned, it's the largest energy storage system in the world. It is connected today to the power grid. And the thing that I like here is to think about scales. You know, it spans the length of 3 football fields. It contains 4,500 stacked battery racks, each containing 22 individual battery modules. And it also has 550,000 feet of wires and cables, which is the equivalent of the distance between Philadelphia and New York. So I want you to think about the scale of this. I want to think about all the materials that are into this facility. And again, think about the scale. We're talking about batteries that can release, you know, up to, you know, kilowatt hours, or a limited amount of power in a matter of hours. And these facilities have a role to play. But when we're thinking about that 10% replacement of natural gas by 2050, we then are talking about this end of the spectrum in here. And here is where underground storage plays a role. There are different ways in which we actually store energy today, natural gas or hydrocarbons in general. We can use porous media, either aquifers or depleted fields, and we can use salt formations by leaching salt caverns. But today we're going to talk about mainly hydrogen storage on salt diapirs or salt formations. So hopefully by now I have established the need of upscale or hydrogen storage capacity. As I mentioned, we need around 1,000 BCF of additional hydrogen storage capacity to replace that 10% of natural gas by 2050, and we only have between 5 to 8 BCF today in the Gulf Coast. So this is some work that Simone et al. Published last year in the Solution Mining Research Institute, where they use the USGS salt inventory to try to put together, some sort of an estimate of what would be the capacity in the Gulf Coast of the US for hydrogen storage on salt bodies, right? We're talking about salt domes here. So a series of assumptions, very basic assumptions, were made, and based on that, the estimation is that the hydrogen storage capacity in the Gulf Coast today would be around 2,000 to 3,000 BCF. Okay, only in the Gulf Coast. And remember that for that 10% hydrogen replacement, we need around 1,000 BCF of additional storage capacity. There are a series of criteria that you need to take into consideration. That includes the depth of the domes, the dimensions of these caverns that usually are 100 feet in diameter and 2,000 feet high, especially in salt domes. We're talking about bedded salt, is a different story there. You need some sort of cavern separation, which is what they're trying to illustrate in here. That is around 500 feet. The salt caverns need to be located more than 500 feet from edge of salt. And using this inventory, there are certain things that they took off because there was not enough data. So what are salt caverns, right? And what's the deal with them, right? I mean, so the concept of salt caverns is not new by any means. And it all started with the need for salt brining. So Texas, for instance, has a long story of salt brining in here. And salt caverns, essentially what you do is you drill a well, you inject fresh water, you dissolve the salt, and you produce the brine. And here you have your cavern. So this concept is really not new, and you have probably heard about the Strategic Petroleum Reserve here in the US. They have 4 locations along the Gulf Coast where they have a bunch of salt caverns where they store hydrocarbons, natural gas or liquids. So usually these caverns have a diameter of around 200 feet and a height of around 2,500 feet. And these ones have these dimensions because they are on salt domes. This is just a plan view showing some contours of one of these locations on the Bayou Chalked Up location, where you can see the salt dome in plan view. And then you can see in green the salt caverns. All right, so in one salt dome you can have several salt caverns. This is a seismic line on shore showing you how these salt domes look like. One of the big challenges here, especially in onshore environments, is that the seismic imaging is very poor. So, when I started to look into this, not being a salt tectonic expert, I had the impression from what I was hearing from colleagues that there was this perception that salt domes, in terms of their composition, were relatively quite pure. In fact, as you dig into some of the information, especially operational information associated with these salt caverns, you come to realize that actually there are more impurities and more complications that we don't fully understand today associated with these salt domes. So Oliver Duffy, who is not a stranger to this group, has been researching some of these aspects and giving some talks and so on. But the point is that my punchline in here is that salt domes even in the Texas Gulf Coast or the Gulf Coast in general of the US, they're not that homogeneous as we originally thought. So why am I saying this? And I was mentioning aspects associated with the solution mining industry and some operational experience by these operators. What I'm showing you to the left is one of these SPR sites, one of these strategic petroleum reserve sites in Jefferson County. And what you're seeing here again in the contours is the dome. And then on red, you see some plains or some areas that have been referenced by the solution mining industry as spines, you know, and I don't want to dive too much into the terminology here. But then you can see the location of salt caverns on this dome. And this is cavern 114 right here. You can see that it intersects some of these areas where one of these plains are located, or spines. And while they were leaching this cavern, they encountered 150 barrels of hydrocarbons. So remember, you imagine the thing, right? You're drilling, you are injecting water, you're leaching, and as you're doing that, out of the soil, and you have 150 barrels of hydrocarbons. Cavern 109, which is here, encounter higher than normal pressure during leaching due to the presence of gas. So finding methane in these caverns during these operations is not uncommon, and this is a problem for a variety of reasons, including product contamination. This is particularly important for hydrogen. If you want to keep your hydrogen pure, you don't want that hydrogen to be contaminated by other fluids. But then the question is, where are these hydrocarbons coming from? And is this biogenic? Is this thermogenic? And if it is thermogenic, where this is coming from? The Big Hill oil field is located to the southwest of this dome. And one hypothesis is that somehow this petroleum system kind of finds its way, or fluids associated with that petroleum system finds its way to the insides of the salt dome. So this 3D blocking here is a humble attempt to illustrate the complexities associated with storing hydrogen or other fluids in the subsurface on salt formations, and how the whole ecosystem looked like. Because the important thing is we need to think about co-location of resources. It's not only about the subsurface, but it's also about surface infrastructure and needs. So what we see here is some salt domes. I'm trying to illustrate here some salt caverns. We have a three-way against salt with a gas reservoir, right? We have a producing field that is sending gas to a refinery, to a steam methane reformer that also needs, by the way, water for the process. So we need to figure out where the water is going to come from. We separate the hydrogen from the CO2. Part of the hydrogen goes to market. Part of the hydrogen goes to a salt cavern. And then the CO2 is captured and is sequestered. And here is also interesting because we need to see in the subsurface the relationship between potential areas where we can sequester CO2 and store hydrogen, if we're talking about blue hydrogen, right? Also here, I'm trying to, in a very schematic way, suggest, right, that if we have a working petroleum system around these domes, it looks like from this operational experience that sometimes these thermogenic gases or these fluids find their way inside the salt domes and contaminate, products inside the caverns. So this is something to keep in mind. So some of you might think, well, how do you know if this methane is biogenic or thermogenic? And this is an active line of research that we are developing here at BEG. And I have to mention Drs. Tongwei Sang and Dr. Richard Kyle. And what we're doing here, especially in Tongwei's lab, is refining a methodology to try to extract gases from samples of halite or salt from domes, so that we can do gas chromatography and analyze those gases. So I'm not going to go into too much detailing here because this is a talk by itself. But in this particular case, what we found out is that this gas is actually thermogenic. It's not biogenic. So what are the migration pathways for this methane to get into this salt is an important question. The other thing is, as I mentioned, for this particular cavern here, 150 barrels of liquid hydrocarbons. I don't think this is something that you can generate biogenically. So there is some sort of mechanisms to connect surrounding petroleum systems with the inside of salt domes, right? So I don't think about salt domes as homogeneous halite bodies anymore. The other thing is here at BEG, you know, during the 80s and so on, there was a big DOE project that was tasked with understanding or studying the feasibility of nuclear waste disposal on salt domes. And as a consequence, we have a healthy collection of core where we can see salt. So this is one example from the Battery Dome, where you can see when you look through these boxes that these halite bodies are not completely homogeneous, either in terms of minerals or internal geometries. So in some of these core, you can actually see folds, okay? Here, these are some collaborators from Stephen Austin State University with Professor Julie Blockson. And one of the things that we're doing in addition to the gas chromatography stuff is to try to do XRF to understand the mineralogy and the variations on this core. Another example from our core repository, where you can see examples of salt from different domes and different intervals, and you can see that they don't all look the same. So now we are, you know, into this task of trying to design methodologies that will allow us to characterize and describe this core properly, and also understanding, as I was mentioning, via geochemical analysis, what is in there in terms of gases and fluids. The other thing that you know, people also wonder about is, what is this? How do you make a salt cavern? You know, as I was mentioning, and yeah, you drill a well, you leach, and then you monitor the process using sonar. So this is how a salt cavern looks like in a sonar survey. And in theory, if your salt dome is all homogeneous and nice, you know, the shape of these caverns should be quite homogeneous, almost cylindrical, you know, or conic. But you can see here in an example from Barber's Hill is that after certain depth, you you can see some sort of a plane that is dipping towards you, and the cavern is widening, you know. So the question is, what is causing this? And there are two hypotheses. One is that you might have some sort of a shear zone, that is generating some movement in there, or that simply you have mineralogical differences between the lower part and the upper part of the dome, and therefore, as you leach, you are leaching at different rates. Either way, it's important to characterize this. Another interesting thing with this particular dome is that 25% of the caverns in the dome present this behavior. And this is important to understand in terms of cavern shape and integrity, right? I was talking about the blue hydrogen ecosystem earlier, but if we are talking about green hydrogen, now what we're talking about is having, wind farms or solar farms. Let's think about West Texas, for instance, and that energy will feed an electrolyzer. You will need a whole lot of water. Essentially, you need 9 kilograms of water to generate 1 kilogram of hydrogen. And if we're talking about West Texas, for instance, this is something that we need to figure out where we're going to get the water from. The water needs to be clean. But one idea is, well, maybe we can get some formation water and have some processing plants to clean it to feed the electrolyzers. And then same concept, some of that hydrogen goes to market and then some hydrogen is stored. So how to approach, the research questions associated with this, how do we characterize these heterogeneities or intrasalt heterogeneities? And there is a series of things that we can do. We can look at salt dome geometries. We can look at the cap rock to see hints of potential deformation that can extend to the core of the salt domes. In terms of infrastructure, understanding casing, shear, and deformation, core texture, describing microstructure distribution, the presence of fluids or permanent salt, permeable salt, structure of sediments above or on the flanks of the dome. There are a series of things that can be characterized. And as I was mentioning, Oli from AGL has been trying to talk about some of these aspects. Some people will think, what about seismic? As you can imagine, particularly onshore, seismic is a bit of a challenge because these surveys were not designed to image inside the salt, but the flanks. However, things like reverse time migration can help improve the imaging. And you can see here an example from the White Castle Dome. This seismic volume was acquired in 1996. And you can see here one of the caverns in there. And as the reverse time migration is applied, you can see that the sediment salt interface definition improves significantly, but not too much to see inside. So this is an active also point or line of research. How do we image the inside of domes better? Sonar, radar, shallow radar stuff. What do we do? I don't have answers for most of these questions, by the way. The other thing that we're doing at the State of Texas Advanced Resource Recovery Program, which is the program that I'm leading here at the Bureau, is, as I said, as geoscientists, we tend to concentrate a lot on the subsurface because that's our passion, that's where our technical expertise and strength is. But for this to work, we need to look at the whole system in the subsurface, not only concentrated on hydrogen storage, but also CO2, where to get the water. So that's one component of it. At the same time, what is happening at the surface, in terms of infrastructure, in terms of market development, and so on. And these are extremely important components. So what you see to the left is what I'm starting to call the Texas Blue Hydrogen Map, which is an attempt, and this is version 1, to start to map resources in Texas. And in this case, what you see is the number of wells per square mile, which tells you something about the density of oil and gas production. Like you can see the trends here. This is Eagle Ford, for instance. And then there is a lot of infrastructure in there. You cannot see too well here, so let me zoom in. This is the Gulf Coast. And, what the team has been doing here is collecting data associated with like hydrogen pipelines, CO2 pipelines, natural gas pipelines, location of salt domes that you see in these purple points here. Current hydrogen storage locations within salt domes. We have 3 in the Gulf Coast, and where we have salt caverns that have been used in the past for a variety of reasons, from all purposes, from gas storage to brine mining to liquid condensate storage and so on. So here, just to talk a little bit more about green hydrogen, you know, I see that we are increasing our power generation capacity associated with green technologies, especially wind, you know, is really going well. But the problem is this concept of intermittency and curtailment. You know, there are cycles of wind generation, and sometimes when your generation capacity is really high, you don't have the demand. And the problem of how to store, how to harness that extra capacity is quite expensive, actually. And what this plot here is showing you, this is for the UK. And in 2020, for example, the excess capacity due to wind generation was around 3.7 terawatt hours. And this is not about just turning on and off a switch. There is a cost of this. So the UK government had to pay 274 million English pounds associated with this curtailment. So that's the importance of figuring this out, you know. And again, green hydrogen could be a good option. And in this case, what we're talking about is these maps show you hydrogen potential from wind. And what you can do is harness that extra capacity to feed electrolyzers and you know, break the water molecule and have the hydrogen, and store the hydrogen to use later on when the wind is not blowing. But it's not a trivial task. I think I'm going to stop here, you know, because I would prefer, it has been 37 minutes, or almost 4 minutes already. I would prefer to open up for comments and a discussion.
All right. Thank you, Lorena, for the talk. Very interesting. It's very good to see the opportunities that are available for future work and what you've done so far. So thank you very much. We have some questions in the Q&A box and the chat, so I'll start reading them off. So one question here, I think somebody has given a shot at an answer, but I'll read it out. It says, from Sofiane, is there any risk of fault reactivation when a cave is created? Is there any approach to mitigate this?
That's an open question. I think that the right people to ask that are, I mean, there is a huge community that has been operating in this for decades, which is the solution mining industry. And for anyone interested in those kind of operational questions, you know, I recommend looking at the Solution Mining Research Institute literature. There have been instances in which, you know, cavern collapse and things like that have been reported. But I want to be careful in comments in here because solution mining and storage of hydrocarbons and all kinds of products in salt caverns have been going on for decades. So the technology behind that is feasible. My question is, you know, as I said, we will need to build probably thousands of extra caverns. You know, the upscaling is quite something. And as everything, the more you do something, the more risks you have to have operational problems, right? So that's why it's important to do more research to be able to answer those questions more accurately.
Thank you. Another question we have here from Josie is, how does vertical migration of salt impact cavern integrity?
Exactly. I mean, those are the, hold on, you know, until research is done, and we'll get back to you. But that's exactly, that's why I was saying with this presentation, I'm not providing answers. I'm just stating questions. If I had to hypothesize, right? And again, take this from a not so tectonic expert, I do believe that one feasible hypothesis is that there is still movement on some of these salt masses. We're not talking about major salt tectonic movement, or tectonic scale movement, but I believe that maybe there is a chance for some still sharing and movement inside these salt domes. But I don't know. The question is, we need to do the homework, we need to do the research, and hold on that.
Thank you. So one other question we have here is, do you have any data? This came early in the presentation, so maybe you may have covered this in your presentation, but it says, do you have any data on geological hydrogen production?
Yeah, that's it.
So it says H2 produced together with hydrocarbons.
Yeah. No, that's a really good question also. And essentially that's what they call white hydrogen, which is essentially naturally produced hydrogen. And there is a bunch of people working on that. There are some areas like in Mali where you have like seeps of hydrogen, that suggest that similarly to hydrocarbons, you could explore for hydrogen. I'm a little bit, I don't want to say reluctant, but so far it doesn't look like these are volumetrically significant reservoirs of naturally occurring hydrogen. But there is a whole lot of research on it, and maybe there is, I don't know. A lot of this is also can be associated with serpentines and mafic, ultramafic rocks. So there is still a lot of research to do on that chapter 2.
Cool. Thank you. Another question here is fast-moving salt a different composition to halite or a different temperature?
Salt formations, and here I have been talking only about salt domes, but salt formations are not homogeneous, so you can have an entire suite of mineralogical composition in there. One, for instance, is anhydrate, and I didn't talk about that. You can have anhydrate as part of these salt domes or bedded salts. And that one is particularly important to understand also because if you have hydrogen interacting with anhydrate, then you can generate H2S, right? So you don't want that to happen. And that's what I'm saying, that for the storage of hydrocarbons and natural gas, we have done a lot, but for the storage of hydrogen, there are still a lot of open questions that we need to understand before we can upscale this technology.
Right, yeah. So as we can see, from the discussion, it seems like there are a lot of open questions that need to be worked on, and it's good that it's good that the presentation sheds light on these questions that we need to be thinking about for the future.
Yeah. No, and I think Tiago Alves, I can see the chat here, is also making a very good point, that the hydrogen is unstable and a whole lot more reactive. And he's asking if there is any experimental data. There are other groups here at BEG that plan to do that, to take samples of salt formations, different compositions, different types, and go to the lab and try to expose that to hydrogen and see what happens. And I think this line of research is going to be extremely important to understand that better. Yeah.
Yeah, so one question before Tiago's question was from Wayne. Have you identified suitable unused salt domes for hydrogen storage? You cannot expect to use existing natural gas storage sites or utilize salt formations in areas with existing oil and gas fields.
That's a really good question. And yeah, there is also talk about repurposing salt caverns that are used for natural gas storage into hydrogen. That's something that it is I want to be careful because there is a lot of engineering. I mean, it is feasible if you do the studies, and it can be attempted. But again, each dome is different, you know. So the thing that is breathtaking for me is that even if you repurpose, let's say that we repurpose all the existing salt caverns, you know, in Texas or the Gulf Coast, still we're short in terms of storage capacity. That's the message that I want to leave here, you know. And the thing that I'm not talking about is in terms of the broader, bigger picture of the hydrogen economy, is that if this is going to work going forward, it's not only hydrogen storage and salt formations. That's the first step that we need to do, and it's challenging by itself. But that restricts the areas where we can store hydrogen to where you have salt, to the geology, to the geography, right? So a very active line of research is hydrogen storage in porous media, meaning depleted gas and oil fields and aquifers. And in there, the challenge is even bigger because that's where we know less, you know. And depending on how you see this, is good news and bad news. It's bad news for the energy transition in the sense that we don't have all the technologies in place to accelerate implementation. But as geoscientists and petroleum engineers or anyone working in the subsurface, it's good news in the sense that we have a challenge in front of us, and we have a lot of work to do to figure this out, because this is not going to be figured out without geoscientists and petroleum engineers, you know. So that's my other message here.
Thank you, Lorena. One question from Willie is, how much water will be necessary to dissolve salt domes to create this?
That's a good question. A lot. You know, I don't have all the numbers right in my head, but I think is 8 parts of water for 1 part of cavern, you know. So that's a lot. And from an environmental perspective, it brings up a challenge, because then the question is, what do you do with the brine, you know? So there have been cases where the brine is just dumped into rivers or stuff. That's not a good thing, okay? And again, if we want to upscale this, we need to find ways to manage this. So the right way, I guess, to do this is to re-inject the brine into a formation, you know? But now, once again, think about complications and think about cost. And think about the level of characterization that the subsurface needs to have in order to be able to do this.
Thank you. So this question involves safety. So I would like to ask how we manage the induced seismicity from the hydrogen storage. It may cause the instability of the hydrogen storage.
That's something that I'm not, you know, that's something that I haven't looked into. But, you know, I would think that, especially for salt domes, I mean, as I said, for decades, we have been using these salt domes to store all kinds of fluids. And I don't think seismicity has been an issue there. But as we upscale this, and as we use also porous media, that's something that needs to be investigated. But at this point, I particularly don't have too much to comment or share. Yeah.
Yeah, we have one question about, this relates kind of to the quality of the reservoir. So the question is, are salt domes practically better than other formations? For example, sandstone reservoirs, shales, to store and extract hydrogen?
Mm-hmm. Yeah, well, let me see if I can go. I think I was mentioning this, and I concentrate on salt because of the audience, but essentially this subsurface storage you can do using either salt formations, and here I was very specific talking about salt domes, but we also have layer salt formations, right? But you can also use porous media that is either aquifers or depleted fields. So we use aquifers and depleted fields to store hydrocarbons or natural gas. And the principle comes from, well, if you have a reservoir where you are extracting gas, obviously that reservoir can also hold gas, right? The problem with hydrogen, again, as we were mentioning, is that hydrogen is very, very tiny. The diffusivity is a whole lot greater than methane. And not only that, but it's very reactive. So if you have a porous media, you have more minerals and more heterogeneities and a higher chance of that hydrogen reacting with that and creating other problems. Or creating H2S, or because the diffusivity is higher, maybe your cap rock or your seal needs to be tighter. So that's a very active line of research in addition to hydrogen storage on salt bodies. But ideally, I mean, the ideal scenario is that you have a salt dome that is 100% halite. Great, that's a great place to put hydrogen in. But my point is that's not always the case,
Thank you. Yeah, so I'll jump into the Q&A box. We have, is there a risk of hydrogen leak through the wells that are drilled to salt cavern?
Yeah, the other thing, again, going back to the reactivity and the chemical characteristics of hydrogen, I don't know if you saw some of these maps in detail, because there is a lot to talk about in here. But like this thing in purple, these are hydrogen pipelines, okay? And the ones in gray, these are natural gas pipelines. There is a reason why there are hydrogen pipelines, is because they need to be built they are specifically designed to handle hydrogen, because the hydrogen molecule is so small that you need a special type of steel and so on. So going back to that question, again, from the drilling engineering perspective, your well design needs to be quite specific, because your equipment and the casing and the type of tubing that you use, it has to be special to be able to handle hydrogen, just because of hydrogen properties. So that's another engineering line of research. The other concern is because the diffusivity of hydrogen is so high compared to CO2 or methane, and it has to do with the size of the molecule. Let's say that we figure out how to store hydrogen on a depleted reservoir, for instance. So we start to store hydrogen in there, but this depleted reservoir had production wells or exploration wells all over the place. If they're not properly plugged, in theory, I guess, you could have migration pathways going through the porous media, reaching those wells and having some leaks. So that's another question that we have. How do you handle that? So again, more questions, no answers.
Yeah, and it's kind of interesting because, in the Gulf Coast, there are so many faults, and if we are doing this in an area with so many faults and the seismic imaging is not allowing us to resolve some subseismic faults, how do we, I guess.
Yeah.
Additional risk, yeah.
Yeah, and I think you're touching here in a point also, or introducing a topic that is important. I oftentimes try to be careful when we talk about that, because if you talk to the general public and you talk about hydrogen, it's like, oh my God, hydrogen. Same thing with CO2 sequestration, right? No one wants to have CO2 sequestration in their backyard. But I think we need to be careful in saying, well, it is. I do believe that it's feasible. Is how you manage risk and is how you characterize the subsurface. I think that needs to be the message. And also, maybe for hydrogen storage, you don't need to have all the time 100% hydrogen, which is more complicated to handle, because that would be for fuel cell, consumption. But the real impact of hydrogen in the broader energy transition context is how to use hydrogen to abate or to help with hard to abate industries like cement, for instance, and in that case, you don't need 99% hydrogen. You can have a blend, you can have something that also have some methane on it or some other stuff. So I think, yeah, we have an interesting challenge ahead of us, one that will need really a multidisciplinary approach and open minds and the willingness to work not only with geoscientists or the subsurface, but also working with engineers and economists. And because a lot is said about the hydrogen stuff, but the market for hydrogen is not there. And the investment to make it work is huge. So it's not as simple as it sounds, So I think we have a long way in front of us, but it's interesting.
Yeah, so we have a question here about a public database. Is there a public database that shows maps of salt domes and other data resources? Someone has taken a stab by mentioning the shapefile from the USGS, but I don't know if you know any other resources.
Yeah, I mean, if you see the work of Simone, which I think Alexandra is here. I think I saw her name somewhere here in the chat. I think she used the USGS public database, so you can access that. Here at the Bureau, as I mentioned, because we had this legacy data from the 80s, not of it digitized, we actually have a spectacular archive of information on individual domes as well, not only location, but also specific characteristics, so that's the data that we're trying to mine and digitize at the moment. So if you have questions about that or interest, in joining our GeoH2 effort, please reach out to me.
So there's a question, it's a bit long, so let me read it out. Incredible challenge to identify variations in salt zones. Have you ever visited a salt mine to see extreme heterogeneity? As the hydrogen molecule is so tiny, isn't the danger of leakage from storage facilities and pipelines higher with extremely explosive consequences? Seems a no-brainer. It is very expensive to make, very expensive to store and ship, and very dangerous. Why not just use methane and store the CO2? So I guess that's a question about, is this really worth all the trouble, I guess?
Yeah. I think we are making a mistake in thinking that the solutions are either keep doing what we're doing, how we're doing it, or completely stopping what we're doing and switching to hydrogen or renewable energies or so on. And the answer is not in either of those extremes. We need both. From a technical perspective, I'm going to be clear with this. I mean, I do believe hydrogen production and hydrogen storage are possible, they're feasible, they're doable, and you can do it in a safe, reliable manner. There is a lot of work to figure it out, yes, but it is doable. Why I think is worth engaging on this line of research, because it is true that CO2 emissions are harming the environment, and therefore we need to find solutions for that. Is it going to happen overnight? No. So that's why we talk about the energy mix. I think these net zero, claims by 2050 are very ambitious. I wish they were achievable, but based only on this small piece, that has to do how to upscale. Who is going to make 1,000 salt caverns from now to 2050? I want to know. How close are we from resolving this whole question about hydrogen storage feasibility in porous media? If someone has an answer to that, no, right? Is it a problem? Yes, it's a problem, but it's a good. I mean, as a geoscientist, this is a problem that I want to work in, and I think it's also good for job security. So, So that's the other thing, you know, especially talking to early career researchers or prospective students. It is worrisome to see that people are shying away from geosciences or petroleum engineering, thinking that these professions are not relevant anymore. When in fact, I think now more than ever, we need that kind of expertise for a variety of things, including hydrogen, CO2 sequestration, geothermal. But it is true that the new professional needs to retool and be open to incorporate elements of engineering, you know, geochemistry, geophysics, different things, you know. So I think that's important.
Excellent. Thank you. Yeah, so I think we have one more questions, or it's more of a comment. It says that we will need to find more salt domes in order to store more hydrogen. So I think, yeah, Lorena, I don't know if you have any comment or a response to that comment.
I think salt domes are fun, man. They're good. And then the other thing that we didn't touch on here is we are talking about onshore environments, but there's plenty of salt offshore. So that's another thing. And again, bedded salt is because in Germany, I mean, right now, and again, to kind of start to wrap up, I guess, as I said, the message here, one of the key messages is the need to upscale hydrogen storage capacity is massive, right? Again, keep that number in mind. Numbers are important. 10% replacement of natural gas, only 10% would require 1,000 BCF of additional storage capacity. We only have 5 to 8% BCF. Right now, around the world, we only have 4 places in the world where there are ongoing hydrogen storage. That one is Teesside in the UK, and then 3 locations in the Gulf Coast: Spindletop, Moss Bluff, Clements. This hydrogen is mainly used for refineries, you know, to get rid of sulfur and for fertilizers and so on. And the other component of this is that the hydrogen that is stored in there is mainly strategic, meaning that they store the hydrogen, but sometimes they don't withdraw the hydrogen for years. What we're talking about in here is if we want to use hydrogen for systems, day-to-day systems, we will need to inject and withdraw hydrogen more frequently, you know. So what is the effect of that on the salt formations is something that we don't fully understand, and that we are also researching here at the Bureau with a couple of our engineers. So massive, that's the conclusion.
Really cool. So I think I missed the question, which you may have touched on a little bit. Says, do you know the state of the art at the national level for hydrogen storage compared to Texas? So I think the question is about what's going on in the rest of the country. Are there other storage sites compared to, and how do they compare with Texas here?
There are salt caverns in different states, including on the Northeast, but most of those, well, let me take that back. There are storage locations, but for other things other than hydrogen. You know, there's no, in the US, besides these 3 locations that I'm showing here in the map, Spindletop, Moss Bluff, and Clements, there is no hydrogen storage on the subsurface. I suspect that, I'm pretty sure several groups are trying to figure that out. But this is where we are right now.
Cool, thank you. Just to mention, Lorena, you did get a few shout outs in the chat, thanking you for the great presentation.
Thank you.
Thanking you for highlighting the future work that is left that needs to be done and all that. So very interesting. Thank you so much.
Thank you, guys. Thank you, everybody.
Thanks a lot, Lorena, and thanks everyone for joining today. It was a great way to end the season 4 of AAPG South Basins webinars. So we'll have an interval of a couple of months now, but we are ready to start planning the series 5 of webinars. So if anyone in the audience would like to present a webinar, please reach out to us. And that was great. Thanks again, Lorena.
Thank you. Thank you for the invitation. And I want to commend all the organizers of these sessions for the massive amount of work that you guys do to engage us on these talks. Thank you.
Thanks a lot. It's been great. Thank you so much.
All right. Goodbye, everybody. Thank you.
Bye, everyone.